So far in this pack, we've seen quite a lot of information about aluminium. So we started off with aluminium as an element, was a giant metallic structure. We reacted it with oxygen. We couldn't react it with water because of its aluminium oxide layer, which is insoluble, but when we reacted it with oxygen to form aluminium oxide, we then looked at aluminium oxide, which is an ionic structure but with significant covalent character. So therefore aluminium oxide could act as a base like other metal oxides, other ionic oxides, but also as an acid like other covalent oxides can. So it was able to be this thing called amphoteric, able to act as an acid or a base. What we're going to look at now is the acidic nature of aluminium salts. So aluminium oxide could be an acid or a base. Now we're talking about aluminium salts. And when we're talking about aluminium salts, we're talking about things like aluminium chloride. That's the salt. Remember, that would be made from hydrochloric acid. Salts are when the H plus of an acid is replaced by a metal ion. We could be talking about aluminium nitrate, maybe aluminium sulfate, aluminium phosphate. So these are all salts. And remembering that because these salts are ionic, they're soluble. And because they're soluble and containing a metal, then they're going to split up in solution, and so we're going to have the Al3 plus ion free from the ionic lattice in solution, and that's what we're interested in. It's that Al3 plus that is able to form acidic solutions. So Al3 plus here, ions, become surrounded by water. They're going to get surrounded by 6 waters, hexa-aqua ion we call it. And we get this formula Al bracket H2O6, and then we have some square brackets around that to show that this is something called a complex ion. It's a metal ion surrounded by some small molecules that are forming coordinate bonds. The whole thing is an ion. So actually we could even imagine that in our aluminium chloride we've got this ion here, and then we've got 3 chloride ions. Or if we were talking about aluminium nitrate, we'd have 3 nitrate ions. So each aluminium is surrounded by 6 water molecules, so hexa-aqua. So 6 hexa water aqua, hexa-aqua ion. And each water molecule is bonded by a coordinate bond, because remember that the aluminium Al3 plus is electron deficient. It's got 3 less electrons than protons, so it's electron deficient. And water has a lone pair on the oxygen. So both of the shared pair going to come from the oxygen. And that's the definition of a coordinate bond. And remember that we can draw coordinate bonds as arrows. So if we wanted to, we could draw arrowheads pointing towards aluminium, because oxygen had the electrons and aluminium was electron deficient. Now, it's this complex that allows us to be acidic, because remembering that the definition of an acid is a proton donor, then why is this acidic? Well, it's these water molecules that are going to donate the proton. So the charge on aluminium 3 plus, aluminium 3 plus is small for how many shells it's got, because it's 3 plus, so its ionic radius is smaller than the other Na plus and Mg2 plus in the same period. So it's small and highly charged, and so it's going to cause the electron density in the water molecules to move closer to the metal ion. So the water molecules, if you could imagine, originally the water molecules had like this spherical distribution of electrons in shells around them, and now it's going to be unevenly distributed. So we're going to imagine that the aluminium 3 plus is pulling the electron density closer to it, so it's polarizing. The electrons are coming closer to the aluminium. In those bonds, they're coming down through the bonds and towards the aluminium. We say the water molecule is polarized, remembering that means that we've got a delta minus end towards the aluminium, delta plus end away. So we're pulling the electrons in. Aluminium 3 plus has enough of this polarizing power. It's small and highly charged, And what it is able to do is break specifically, let's highlight that, the OH bonds in water. And so we're going to break this bond here with this curly arrow. We can see it being broken. So the aluminium is pulling the electrons through the water molecule. They're sort of coming this way towards the aluminium, and it's weakening this bond here. And so we can say that that bond's going to break, and the proton here is going to be released. Oops, I'll do an actual pen. So we've got a proton donated, and that's what makes us acidic. We could write this equation out so that we wouldn't have to draw it all out in the exam. We could write it as aluminium, 6 waters, with that 3+ charge. That's all on the aluminium ion, coming from the aluminium ion in the middle. We've now got 5 full water molecules, but one of them has lost 1 hydrogen, so it looks like a hydroxide ion. And because of that, we've lost 1 hydrogen ion. The charge on this complex has gone down by 1. The aluminium in the middle is still 3+, but we've now got 5 neutral water molecules and an OH minus. And so we've got this H+ that has been donated. So these aluminium 3+ ions are proton donors in this way, and therefore they are acidic. Okay, so what happens then is if they're acids, then you could react them with bases. So if we were to take, we're saying that this is an acid, aluminium H2O6 3+, that's our acid, that we could then react that with a base, OH minus, from say sodium hydroxide, and we could make Al H2O 3 times, OH 3 times. Notice that this would not have a charge. Now we put a 3 here, 3 pluses on the aluminium ion, 3 hydroxides to react that. And that would go all the way. Now, because that is charged, that must be AQ, because the only way you can show ions in an equation is if they are ionic and aqueous. So these two must be AQ, but this neutral molecule here is uncharged, and because of that, they're able to attract one another, and then they precipitate out as a solid. And that would be our overall equation for what is happening. And we'll notice here it says insoluble precipitate. So we've got a colourless solution of aluminium 3+. We've got a colourless solution of sodium hydroxide or potassium hydroxide. And then all of a sudden we mix those two together and we form a white precipitate of aluminium hydroxide. So this is aluminium hydroxide. It is, since it is a neutral molecule, has no charge, it becomes insoluble. They're able to attract each other, so it's insoluble, not repelling each other anymore, and a white precipitate will be seen. Now this aluminium hydroxide is now something that is able to react as both an acid and a base. So we had the aluminium oxide was able to act as an acid and a base, and now the aluminium hydroxide is able to act as an acid and a base. It was the aluminium salts, just Al3+ ions, that were acidic. So it's quite, I can understand it can be quite hard to keep these separate in your head, but you just need to keep working at it, keep trying, practicing in questions to make sure you're remembering which times something is amphoteric and which times something is acidic. So aluminium hydroxide, which we can show as having the 3 waters and the 3 hydroxides. So, or we can sometimes we'll see it simplified. And when we see it simplified, it might be what you would think to write for aluminium hydroxide, which is just AlOH3, so aluminium ions and hydroxide ions. or you can show it as the complex with the 3 waters as well. So it can act as a base. Okay, so if aluminium hydroxide is the base, I'll do the full version first and then a simplified version. So here's our base. Then that means it can react with an acid. So we'll just have a generic for acid as H pluses. And if it reacts with acid, all 3 of these hydroxides will turn back into waters, and we will regenerate the aluminium hexaaqua ion. And so remembering that this was a solid, a white precipitate, and this was a solution, and now it's charged, so this is a solution. And so the white precipitate of aluminium hydroxide dissolves and we form a colourless solution. And this reaction, along with the reaction for the formation of the hydroxide, come together to be the test for aluminium ions. Because how do I know which colourless solution is which? Well, one of the ways to find out if it's aluminium is to add hydroxide ions when you'll see a white precipitate, and then it will redissolve to form a colourless solution. We'll write that down in a minute in the extra notes page, just so that we've got it down. So that was our full version. We can simplify that equation if we like to get rid of the extra waters, but it doesn't always help. I think that the top one is a good equation, but you could do this and make it be like Al3 plus and 3 waters. To be fair, I wouldn't usually use that version. I would stick to the one at the top. So I am going to take that off, but it's just to show you that you could do that, but I would normally stick to that first one. If we then say, well, what if aluminium hydroxide acts as the acid? How is it able to do that? So this time I'm going to have it as the acid in red. I've got the 3 waters and the 3 hydroxide ions. Remembering that that is a white precipitate. And this time, if I add hydroxide ions, we're not actually going to pull off the 3, makes it go to having 6 OHs and pull off H's off 3 more of the waters. Because after I would have formed this product, and I've just realised I need to change that to the colour for base. So this was my aluminium hydroxide added as an acid. If we have a look what happens when we add 1 hydroxide ion, then we'll pull 1 more hydrogen off 1 more water, 1 more hydrogen ion, so we end up with 2. And now we've got 4 OHs, and now the whole thing becomes 1 minus. So if I were to try to add another OH minus to it, then the OH minus and the aluminate ion that we've got here, the AlH2O2OH4 1 minus, they would repel one another, and so you wouldn't be able to add a second one. So we've here got aluminium hydroxide, which was our colourless, white precipitate. And it's formed because it's gone charged, remember when it's got that charge, it wouldn't be a solid. To have a charge in an equation, it must be AQ, which means it must be a solution, and it's a colourless solution. So it dissolves to form a colourless solution. And then this one does get simplified quite a lot in exams, because if you use the aluminium hydroxide as just AlOH3, and then you add the OH minus, then you can form the AlOH for aluminate ion, which we saw and we wrote on the front of our pack as the negative ion formed from aluminium oxide as well. So we've seen that one before. So it is sometimes simplified like that. So aluminium hydroxide reacts with both acids and bases. It is amphoteric. What we're going to do now is I'm going to leave the summary page. That's something that you can fill in and check on Moodle, but we're going to just skip to the additional notes page, and we're just going to write a little note to ourselves for the test, and this is part of one of the required practicals later in the course, but it's good to have it here, testing for aluminium 3+ ions in solution. So this is not how you test for aluminium. Aluminium is a metal. You don't test for aluminium this way. This is how you test for aluminium 3+ ions in solution. So you've got a colourless solution. You suspect it might contain aluminium ions, so it might be something like aluminium sulfate, aluminium chloride. Then what you would do is add sodium hydroxide dropwise until in excess. And if it's aluminium ions that are present, if Al3+ ions are present, a white precipitate forms which dissolves in excess. So if we were to sort of write that as equations, we've got aluminium 3+ ions. Remember that in solution they're as the hexa-aqua ions. We're adding sodium hydroxide a bit at a time, and we get a white precipitate. And then when we add a bit more in excess, then we can add that one more. And when we add that one more, we see that we get the aluminate ion with the 4 OHs, the 1- charge. And because that is charged, then that is going to be a colourless solution. So this is our test for aluminium ions. So in this video we've covered how aluminium salts, so Al3+ in solution, is acidic. There we go. And just notice there, so just make sure you go back that there's a 3H2O missing there. And that it forms a white precipitate, and then that hydroxide ion is amphoteric, so can react with acids and bases, and how this can be used as a test for aluminium ions. So make sure that you go over this video carefully and you fully understand what's going on. If not, you need to speak to your teacher and they'll help you with this section.